All right, let's talk about a chemistry concept that trips a lot of people up, limiting reactants and percent yield. But what if I told you the secret to totally getting it is as simple as making a cheese sandwich? Yeah, really. Let's dive in. So, I know what you're thinking. What on earth do cheese sandwiches have to do with chemistry? It sounds a little weird, I'll give you that. But trust me, this simple idea is the key to unlocking this whole topic. You'll see exactly what I mean. Okay, so first things first. Let's imagine our perfect cheese sandwich recipe. It's super simple. You need 2 slices of bread and 1 slice of cheese. That gets you 1 sandwich. That ratio, 2 to 1, is our golden rule. Okay, now for the fun part. Picture this. You're in the kitchen, ready to make lunch. You've got 7 slices of bread. Plenty, right? But then you look in the fridge, and you only have 2 slices of cheese. So, thinking about our recipe, how many sandwiches can you actually, truly make?
That's right, just 2. Even though you have enough bread for 3.5 sandwiches, it doesn't matter. You're gonna run out of cheese after you make the second one. The cheese is literally holding you back. It's the bottleneck.
And that right there, that's the core idea. The cheese is what we call our limiting ingredient. Why? Because it's the one that runs out first, and it's the one that dictates the total number of sandwiches you can possibly make.
Okay, so let's swap our chef's hat for some lab goggles. We're taking this exact same idea and walking it from the kitchen right into the chemistry lab. Instead of ingredients, we're going to call them reactants. And instead of a sandwich, we're making a product. The principle, though, exactly the same.
So here it is, the official term, the limiting reactant. It's simply the substance in a chemical reaction that gets completely used up before anything else. Just like our cheese, it effectively stops the reaction and puts a hard cap on how much product you can form. And all that leftover bread? Well, chemistry has a name for that too. It's called the excess reactant. It's all the stuff you have extra of, the stuff that's just kind of sitting around after the reaction stops because its partner, the limiting reactant, is all gone. Okay, so theory is one thing, but let's actually put this to the test. It's time to solve a real chemistry problem and figure out how to mathematically find that limiting reactant. So here's our reaction for today. We're reacting magnesium with hydrochloric acid. Now that balanced equation up there, that's our recipe. It tells us we need 1 part magnesium for every 2 parts of HCl. Now let's say we have 0.30 moles of magnesium and 0.52 moles of HCl. Which one is our cheese and which one is our bread? You know, finding the limiting reactant sounds way harder than it is. It's a super simple 3-step trick. First, you just take the moles you were given. Second, divide that number by the coefficient. You know, the big number in front of the molecule in the balanced equation. And third, the smallest answer wins. That's it. That's your limiting reactant. Okay, let's run our numbers. For magnesium, we have 0.30 moles, and its coefficient is just 1. So 0.30 divided by 1 is, well, 0.30. For hydrochloric acid, we have 0.52 moles, but its coefficient is 2. So we take 0.52 and divide it by 2, which gives us 0.26. And there we have it. Because 0.26 is the smaller number, hydrochloric acid, HCl, is our limiting reactant. It's the chemical that's going to run out first and stop this whole reaction in its tracks.
Now this is absolutely crucial. That smaller number we just calculated, the 0.26, that's not just a random number. It tells us the absolute maximum amount of product that can possibly be made. So in this reaction, we can form at most 0.26 moles of hydrogen gas.
So the math gives us a nice, clean, perfect number. But here's where chemistry gets really interesting because the real world, the actual lab, is often a little bit messy. What you expect on paper isn't always what you get in reality. This brings us to 2 new, really important terms. First, there's theoretical yield. Think of this as the perfect world calculation. It's the absolute max amount of product you could ever make based on the math. Then there's the actual yield. That's the real world result. It's the amount you physically collect and weigh after you've actually done the experiment. And here's the thing you have to know. In almost every real experiment, the actual yield is going to be less than the theoretical yield. Maybe the reaction didn't fully finish, or maybe a tiny bit got lost when you were transferring it. You know, it happens. So if you almost never get what you expected, how do chemists measure how well a reaction actually went? How do they, grade themselves? Well, they use a fantastic little tool called percent yield. And here it is, the formula for success. It's as simple as it looks. You just take your actual real-world result, divide it by the theoretical perfect world calculation you did earlier, and then multiply it by 100. It's basically a report card for your reaction. Let's run through one last example to make sure this sticks. Imagine we're heating 24.8 grams of calcium carbonate. Our math, our theoretical yield, says we should get 13.9 grams of product. But after we do the experiment for real, we weigh our product and find that we only collected 13.1 grams.
So we just plug those numbers right into our formula. We take our actual yield, 13.1 grams, divide it by our theoretical yield, 13.9 grams, and multiply the whole thing by 100%. So what's our score?
We get 94.2%. Hey, in the world of chemistry, that is a fantastic result. That tells us our reaction was super efficient, and we successfully created over 94% of the maximum possible product. That is definitely a win. So, what's the big takeaway here? This stuff isn't just for your chemistry class. Understanding what limits a reaction and how to measure its success, that is absolutely fundamental to all of chemistry, whether you're creating life-saving medicines or developing the next generation of new materials.
So, I'll leave you with this to chew on. Now that you know how to spot a limiting ingredient, whether it's cheese in a sandwich or a chemical in a beaker, what other hidden limits might be shaping the world around you? In technology, in economics, maybe even in your own daily life. It's a powerful way of seeing the world,